Hello, my name is Tor-Salve and I will present the paper Modeling Pointing for 3D Target Selection in VR, created together with Jarrod Knibbe and Joanna Bergström. In the real world, humans interact only with objects that are in reach due to the natural restrictions of their arm's length. In virtual reality, humans also interact with objects within arm's reach, but due to the freedom in the virtual world, humans can use more or less realistic transformations to the body to select objects. For instance, the classical go-go technique does elongate the virtual human arm to select distant objects. Another technique is raycasting, where a potentially straight line is originating from the human's body, intersecting these targets. But augmenting the body is not always desirable, and using raycasting techniques are not particularly accurate, as the normal human pointing is not accurate. With this technique, humans need to adjust to the system, as they are in charge of correcting these natural errors. We know from previous work that the pointing error is systematically inaccurate, meaning that we can create models for correcting those errors. And inspired by this previous work, we examine cursor-free pointing in order to derive a model of how humans would naturally point at a 3D target space. The aim of our work is to analyze the movement data of humans to determine a set of features describing the movement as best as possible. For this aim, we collect movement data from arms and bodies where participants point at targets at a distance. We then do feature selection on the collected data to describe natural pointing movement. After, we estimate the accuracy of the selected features using machine learning techniques. To capture the movement data of humans pointing, we invited participants to point at targets in virtual reality. The 27 targets are spaced 1 meter apart, and they are at a distance across a virtual room. With this, we got hold of 1,755 movement patterns with these 27 targets. From these data points, we generated 3 scenarios, for each of which we generate a set of features. In the first scenario, we limit the data, such that only the posture describing the final pointing position is included. This is motivated by the ease of implementation in a final selection technique. We generate a feature set consisting of positional features, such as the position of the index finger, combined features, such as the shoulder flexion, categorical features, such as indicators whether the hand is above the shoulder, and distance features, such as the distance between the index finger and upper arm. Most oftentimes, the targets in the center row in front of the participants are classified wrong, suggesting that the pose pointing at these targets is very similar across these targets. In a second scenario, we included the full movement. The motivation here is to be able to predict the target ahead of time and to enable continuous target selection without the use of a trigger. The feature set consists of the coefficients of a third-order polynomial fit on the index finger movement and the velocity and acceleration of the exact same index finger. The prediction accuracy is inferior to the previous scenario, although above chance level. As the last scenario, we selected a subset of the pose features, consisting of features that could be tracked with a simpler setup than a full-blown motion capturing system as we use it. This could, for instance, be hand tracking built into a HMD or external devices. The feature set consists of data points on the head, wrist, and hand, and has very similar prediction accuracy to the pose features, meaning that a model using more accessible tracking yields equally good results as full body tracking. So what to do with all of this? Well, we have shown that we can model human movement with relatively simple features. With this model, we can implement interaction techniques that are more natural than what we have now, as we now can give cursor-free feedback on a given selection target. Further, we can expand this work by collecting even more detailed data, such as, for instance, gaze. And all in all, we can reliably determine a selection target based on human movement, which allows for a wide range of applications in virtual reality. Interesting as a next step could, for instance, be to find out how well these models translate into other realities, namely augmented reality or the reality surrounding us in everyday life, for instance, in a smart home setting. But most importantly, using these models, we redistribute the responsibility of adjusting to the system. So now the system needs to adjust and not the human. And with this, thanks for your time and see you around.